There's a moment buried deep inside NASA's classified telemetry archives that scientists have quietly debated for years. It happened in the final seconds, not minutes, not hours. The final seconds of a spacecraft that had traveled over 4 billion miles, survived 20 years in the harshest environment in the solar system, and was now burning alive inside Saturn's atmosphere. In those last moments, the data it sent back did not match what any model predicted. The readings were wrong. Or rather, they were. Too right, too strange, too perfect in ways that should have been impossible, and nobody has fully explained it yet. There is something deeply unsettling about the way scientists describe the final seconds of Cassini's life. Not sad, not emotional, though those feelings were certainly there in the room. The word that kept surfacing, quietly, almost reluctantly, was unexpected. And in the language of planetary science, that single word carries the weight of 1,000 unanswered questions. On September 15th, 2017, at precisely 7:55 and 46 seconds Eastern Time, a signal arrived at NASA's Deep Space Network antenna in Canberra, Australia. It was the last transmission from a spacecraft that had become, over 13 years, one of the most scientifically productive machines humanity had ever built. 1 minute after that signal died, Cassini ceased to exist as a physical object. It had been torn apart by atmospheric friction, its titanium frame and gold foil and scientific instruments reduced to superheated vapor, absorbed into the very planet it had spent its entire operational life studying. NASA officials expected that Cassini broke apart about 45 seconds after that final transmission, due to the intense friction and heat generated by the fall. The spacecraft was gone, but the data it sent in those final moments, that was only just beginning to be understood. What most people are not seeing is this. The end of the Cassini mission was not the end of the Cassini mystery. It was the beginning of one. To understand why those final seconds matter so much, you need to understand what Cassini was doing during the 5 months before it died. In April 2017, NASA's Cassini spacecraft began writing the final, thrilling chapter of its remarkable story, its grand finale. Every week, Cassini dived through the approximately 200-mile wide gap between Saturn and its rings. No other spacecraft had ever explored this unique region. Think about what that means. For billions of years, that narrow corridor between a planet and its rings had existed in complete isolation. No probe had ever threaded through it. No human instrument had ever sampled the material there, measured the electric currents flowing through it, or touched the charged particles drifting in that strange, pressurized darkness. Cassini did all of that, 22 times in a row, on a trajectory that grew increasingly dangerous with each pass. And on the 22nd pass, it didn't pull back. It went all the way in. Atmospheric entry began about a minute before loss of signal, and the spacecraft sent scientific data in near real time until its antenna could no longer point towards Earth. 8 instruments were streaming live during that final descent. The mass spectrometer was tasting Saturn's atmosphere for the first time in history. The magnetometer was recording magnetic field strength at depths no sensor had ever reached. The plasma wave instrument was listening for electrical activity in the upper cloud layers. Every second that passed added irreplaceable data to the archive. And then the atmosphere thickened. The drag became too great. The thrusters that kept Cassini's antenna pointed at Earth were overwhelmed. The signal vanished. The mission was over. Initial results indicate that hydrocarbons appear to be descending into the atmosphere from the rings, that electric currents flow between the inner rings and Saturn, and that a new radiation belt exists in the gap and innermost ring. This alone was stunning. Electric currents flowing between the rings and the planet. A direct electromagnetic connection between Saturn's ring system and its atmosphere was something theorists had speculated about for decades but never directly confirmed. Cassini confirmed it. And the existence of an entirely new radiation belt in a region everyone assumed was empty? That was not predicted by any model, not one. Scientists had mapped that gap using every tool available before Cassini flew through it. They believed they understood what was in there. They were wrong. The real story, according to informed planetary scientists, is far more layered than the press releases suggest. The deeper you go into the grand finale data, the more questions emerge that simply do not have satisfying answers yet. Start with a magnetic field. This was supposed to be one of the cleaner problems in planetary science. Measure the field from close range, map its structure, determine the internal rotation rate of the planet, and move on. Simple, elegant. Except the result that came back broke the rules of planetary physics as they were understood. Based on data collected by Cassini's magnetometer instrument, Saturn's magnetic field appears to be surprisingly well aligned with the planet's rotation axis. Previously, mission scientists thought that 0.006 degrees would be the lower limit of tilt that could generate the observed magnetic field. However, the results show the tilt may be much less than this. Read that again. The tilt, the crucial theoretically necessary imperfection, in a magnetic field that allows it to sustain itself was essentially zero, less than 0.01 degrees. Scientists currently held the belief that for planets to generate magnetic fields, there must be a tilt between its rotation axis and its magnetic field axis. This was considered necessary to sustain currents flowing through the liquid metal deep inside the planets, which in Saturn's case is thought to be liquid metallic hydrogen. Without that tilt, the currents should die. The field should collapse. It cannot maintain itself under the known laws of planetary dynamo theory. And yet, there it was, a perfectly symmetrical, impossibly stable magnetic field wrapping around a planet the size of 9 Earths, behaving in a way that should be physically impossible. Professor Michelle Doherty of Imperial College London stated, "It looks increasingly likely we will have to rethink the ways different kinds of planets can form magnetic fields." When a senior scientist on the Cassini mission says we need to rethink the fundamental ways planets work, that is not a minor footnote. That is an admission that our most basic framework for understanding gas giant planets may be incomplete. Because the magnetic field anomaly is not isolated, it connects to something else, something even more disturbing about what Cassini found in those final orbits. The question of how long Saturn has even existed in its current form, not the planet itself, but the system, the rings, the moons, the entire structure we see when we point a telescope at the 6th planet from the Sun. Cassini's data suggested an answer that nobody expected, and not everyone has accepted it yet. By analyzing 163 grains of dust from outside the Saturn system that Cassini gathered from its rings, scientists estimated the hoops are no more than 400 million years old, and they may still have been forming when dinosaurs roamed the Earth. 400 million years. Saturn itself is 4.5 billion years old, almost as old as the solar system. But its rings, those iconic, breathtaking bands of ice and rock that define the planet's entire visual identity, may have formed long after. The age of trilobites, after the first fish evolved eyes, after the first forests appeared on land. Cassini's measurements of micrometeorite bombardment rates, ring mass, and contamination levels all pointed in the same uncomfortable direction. The rings we see today are cosmically young. Cassini's measurements of the meteoroid influx rate, the mass of the rings, and the inflow rate of ring material onto Saturn were particularly important for determining the age and longevity of the rings with confidence. Think about what that means. If you had looked at Saturn from Earth 400 million years ago, before the rings formed, you would have seen a different planet, a gas giant without its defining feature. Just a pale golden sphere, slightly flattened at the poles, with no spectacular ring system gleaming around its equator. The Saturn of ancient Rome, the Saturn of mythology, the Saturn that ancient astronomers tracked across the sky, they were all looking at something relatively new by cosmic standards. A planet in the middle of a transformation. The theoretical models demonstrate that the rings should be losing mass onto the planet at the prodigious rate of many tons per second that Cassini observed, which means the remaining lifetime of the rings is only another few hundred million years or so. Several tons of ring material, every single second, raining down into Saturn's atmosphere. The rings are not just young, they are disappearing. They are in the process of slowly vanishing. In cosmic time, they are already halfway gone, and no one can fully explain why they formed when they did, or what catastrophic event created them in the first place. One scientist noted, "If we can discover what happened in that system a few hundred million years ago to form the rings, we may just end up discovering why Saturn's moon Enceladus is spewing out from its deep ocean plumes of water, ice, and even organic material. We may perhaps even end up finding the building blocks of life itself on Enceladus." Enceladus, the small ice-covered moon of Saturn that Cassini fundamentally transformed from an astronomical curiosity into one of the most scientifically important objects in the entire solar system. Before Cassini, Enceladus was considered a frozen, geologically dead moon. Too small, too cold, too far from the sun to have any interesting internal activity. The mission changed everything. Key discoveries included a global ocean with indications of hydrothermal activity within Enceladus. Beneath its frozen crust, a liquid water ocean, kept warm by tidal heating from Saturn's gravity, was actively churning and actively venting material into space through enormous geysers near the South Pole. And that material was being analyzed in real time by Cassini as the spacecraft flew through the plumes. And what those plumes contained is what makes the planetary science community quietly nervous. According to informed sources in the astrobiology community, the organic chemistry detected in Enceladus's plumes was not simple. It was not just water vapor and basic carbon compounds. Scientists had previously identified numerous organic molecules in the Cassini data, including precursors of amino acids, which are fundamental building blocks of life. Amino acid precursors, the chemical stepping stones toward the molecules that make proteins possible, detected in the spray of an ocean hidden under the ice of a moon orbiting Saturn. There are many possible pathways from the organic molecules found in the Cassini data to potentially biologically relevant compounds, which enhances the likelihood that the moon is habitable. And in October 2025, new analysis went even further. Fresh analysis of Cassini data revealed new complex organic molecules inside ice grains spewing from Enceladus, strengthening the case that the moon's underground ocean hosts conditions favorable to life. These were not simple molecules anymore. These were complex ones, the kind that take many chemical steps to build, the kind that, on Earth, are associated with biological processes, the kind that do not typically form through simple chemistry alone. This is not proof of life. Let that be absolutely clear. But it is something more unsettling than proof. It is evidence that the conditions for life are present, that the chemistry is advancing in the right direction, and that a world we barely knew existed a generation ago is now one of the most serious candidates for extraterrestrial biology in the solar system. And Cassini, in its final orbits, collected the data that proved it. Now consider the timeline of what you just learned. The magnetic field that should not be stable but is. The rings that should not be young but are. The moon that should be dead but isn't. 3 separate mysteries, all revealed by the same mission, all pointing in the same direction. Our models of how the Saturn system works are fundamentally incomplete. Not wrong in small details. Incomplete in large structural ways. And Cassini's data, years after the spacecraft ceased to exist, is still being used to reveal just how incomplete those models are. Saturn's magnetic field isn't the smooth, symmetrical shield scientists see around Earth. Instead, it's noticeably skewed, and researchers now think they understand part of why. By analyzing years of data from the Cassini spacecraft, scientists found that a key region where solar particles enter Saturn's atmosphere is consistently shifted to one side. This distortion appears to be driven by the planet's rapid spin combined with a thick cloud of charged particles coming from its moon, Enceladus. So Enceladus, the moon spewing water and organics into space, is actively deforming Saturn's magnetic field. The two are connected in a feedback loop that shapes the entire magnetospheric environment of the planet. The moon affects the planet affects the moon. The rings form from the same chaotic system. And all of it, the entire interconnected, dynamic, and deeply strange Saturnian ecosystem, is still being unraveled from data collected by a spacecraft that no longer exists. Cassini may have ended its mission in 2017, but its data is clearly not done revealing secrets. In April 2026, just months ago, a new study published in Nature Communications revealed that Saturn's magnetic shield, the boundary where the planet's magnetic influence deflects the solar wind, sits in a completely different location than any model predicted. Their findings reveal that a key feature of Saturn's magnetic environment sits in a completely different place than where anyone expected, and the reason why changes how we think about giant planets entirely. Not slightly off, not marginally misplaced by the kind of small error that gets quietly corrected in the next paper. Completely different. And the reason, according to the researchers, is that Saturn operates under a fundamentally different set of physical rules than Earth-like planets. Rules that scientists are only now beginning to understand, nearly a decade after Cassini ended. For decades, Saturn's behavior puzzled researchers. Data collected by NASA's Cassini spacecraft in 2004 indicated that the planet's rotation rate appeared to shift over time. That result conflicted with basic physics, since a planet's spin should remain stable and not fluctuate in that way. Think about that. A planet's rotation rate should be one of the most stable, predictable measurements in astronomy. It is determined by the distribution of mass inside the planet, physics that does not change on human timescales. But Saturn's measured rotation rate appeared to change. Cassini recorded values that were different from those the Voyager spacecraft recorded 25 years earlier. Either the planet was actually slowing down, which is essentially impossible, or something else was affecting the measurement. Something in Saturn's atmosphere, or magnetic field, or ionosphere was mimicking a change in rotation that was not actually there. A 2021 study led by Tom Stallard demonstrated that Saturn itself was not changing its rotation speed. It was the atmosphere. Saturn's upper atmosphere, driven by auroral currents and Enceladus's material cloud, was generating electromagnetic signals that mimicked a rotational drift. The planet's winds and electrical systems were so powerful, so complex, that they could fool spacecraft instruments into recording a false rotation rate. And in 2026, a new study using the James Webb Space Telescope confirmed and extended this finding, showing precisely how atmospheric dynamics drive the magnetospheric rotation signal, and finally giving scientists a mechanism that could account for the decades-long discrepancy. But the paper that provided this answer also admitted something quietly important, that without Cassini's data as a baseline, none of the new analysis would have been possible. Without those 13 years of orbiting Saturn, and crucially, without those final 22 dives through the ring gap, there would be no foundation for any of these discoveries. which raises a question that almost no one is asking publicly. The Cassini archive contains an estimated 600 gigabytes of raw scientific data. Scientists have been working through it for nearly a decade, and they continue to publish new papers in 2025 and 2026 based on measurements taken by instruments that have been destroyed for years. The spacecraft is gone. The team is dispersed. The mission is officially over. And yet new discoveries keep emerging from the data, like fossils being uncovered from ancient rock, each one adding detail to a picture that was always more complex than it appeared. Saturn's thermosphere, the uppermost layer of its atmosphere, has temperatures far higher than any model predicted, yet the energy source for this heat remained a mystery for decades. Cassini's final orbits allowed scientists to create a two-dimensional map of temperatures in Saturn's thermosphere as a function of latitude and depth. The observed temperatures at auroral latitudes were cooler and peaked at higher altitudes and lower latitudes than predicted by models. This is what scientists call the energy crisis of giant planet atmospheres. The upper atmospheres of Saturn, Jupiter, and Uranus are all dramatically hotter than they should be based on sunlight alone. Something else is heating them. Saturn receives weak sunlight at its distance from the sun. The energy input should produce cold, thin upper layers. Instead, they are scorching. Cassini's data is helping map where this extra heat appears. But the fundamental source of this energy, the mechanism by which hundreds of degrees of unexplained heat are being deposited into the upper atmosphere, remains an open question. Not a small open question, a foundational one. Because this energy crisis is not unique to Saturn. It affects every giant planet in the solar system. Understanding it at Saturn, using Cassini's unparalleled data, could unlock something that changes our understanding of all gas giant planets, including the thousands of gas giants we are now discovering around other stars. And this brings us to the part of the story where everything that has come before clicks into place, and what emerges is something that should make every person paying attention sit up straighter. The Cassini mission was designed in the 1980s. The instruments were conceived when scientists still thought Saturn's rings were ancient, Enceladus was dead, and the ring-planet gap was empty. The science that justified building Cassini in the first place was based on a model of the Saturn system that turned out to be significantly wrong. And yet, perhaps because the mission was designed based on old assumptions, because it was built to answer questions that turned out to be the wrong questions. It ended up answering questions nobody had even thought to ask. The discovery of Enceladus's ocean was not one of Cassini's primary mission objectives. The detection of amino acid precursors in the plumes was not in the original science plan. The revelation that the ring planet gap contained a new radiation belt and electric currents was not a predicted result. These were surprises, every single one of them. One of the greatest legacies of the mission is not just the scientific discoveries it makes and what you learn about, but the fact that you make discoveries that are so compelling that you have to go back, said Mike Watkins, director of JPL. You have to go back. That phrase is doing a lot of work, because right now, no spacecraft is orbiting Saturn. No mission is actively sampling Enceladus's plumes, or threading through the ring gap, or measuring the magnetic field from the inside. The nearest follow-up mission, a concept called the Saturn probe, or a possible Enceladus, Orblander, is still in planning stages, still competing for funding, still years or possibly decades from launch. The data window that Cassini opened is not currently being exploited by any active mission. We are flying blind again, working from an archive instead of a live feed, trying to understand a dynamic system from a static snapshot. If the rings are young, then most of Saturn's icy moons may be as well, including geyser-spewing Enceladus. Enceladus is widely viewed as one of the solar system's best bets to harbor alien life, and the chances are much better if life has had 4.5 billion years to get going there rather than 100 million. That is the stakes of the age debate. It is not just about ring formation mechanics or dust pollution models. It is about whether or not life on Enceladus had enough time to develop. It is about whether the ocean beneath that ice shell has existed long enough for biology to take hold. And right now, scientists are debating both sides with data that has inherent uncertainties, from instruments that no longer function, gathered by a spacecraft that burned up in Saturn's clouds on a September morning nearly a decade ago. A 2026 reconsideration of Saturn's ring exposure age argued that the standard dust pollution argument depends strongly on uncertain parameters. A Japanese-led study published in Nature Geoscience also challenged the idea that clean rings must be young, proposing that micrometeoroid impacts may vaporize much of the incoming material and leave little dark residue behind. So even the foundational conclusion, that the rings are young, is being challenged again. The very data that seemed to settle the question is being reanalyzed with new models, and the new models are producing different answers, which means that the Saturn we think we understand from Cassini may still be substantially different from the Saturn that actually exists out there. 800 million miles away, surrounded by rings that may be young or ancient, orbited by a moon that may or may not have had time to develop life, generating a magnetic field that no theory of planetary physics can currently explain. This is not chaos. This is science operating at the absolute edge of human knowledge. And those final seconds, those last transmissions that Cassini sent as it tumbled through Saturn's upper cloud layers, as the atmosphere tore at its frame and the thrusters strained to hold the antenna pointed at a dot of light 83 light minutes away. Those seconds contained data that is still being decoded, still being modeled, still producing papers in 2025 and 2026 that rewrite pieces of planetary science. It's common for archival data from spacecraft like Cassini to continue providing new insights long after the craft are no longer operational. Common, perhaps, but never quite like this. Never at this scale, this depth, this ongoing rate of fundamental surprise. What did Cassini's final seconds actually reveal? They revealed a planet that is stranger than any model predicted, a magnetic field that breaks the rules, rings that are cosmically young and vanishing in real time, a moon with an ocean and organic chemistry that points toward the possibility of life, an upper atmosphere burning with unexplained heat, an electromagnetic environment that is still being fully mapped years after the last measurement was taken, and a gap between planet and rings that turned out to be not empty at all, but filled with currents and radiation and complexity that scientists are still trying to categorize. But more than any specific discovery, what Cassini's final seconds revealed is the size of what we do not know, the scale of the gap between our models and reality, the degree to which Saturn, a planet that has been observed by human eyes for centuries, that has been studied by spacecraft for decades, remains profoundly, stubbornly, magnificently mysterious. The next mission to Saturn will not launch for years, possibly decades. When it arrives, it will be carrying instruments designed with Cassini's revelations in mind, built to answer the questions that Cassini raised rather than the ones it was designed to answer. It will find things that Cassini missed. It will confirm things Cassini hinted at. And almost certainly, it will discover things that neither Cassini nor any model we build between now and then will have predicted. Because that is what Saturn does. It waits. It keeps its secrets behind layers of cloud and ice and magnetic complexity. It gives scientists just enough to be certain that there is something more, something deeper, something that the next measurement might finally reach. Cassini dove into those clouds and burned. It gave everything it had, and the data it transmitted in its final seconds across more than 1 billion kilometers of empty space to an antenna pointed at the sky in the Australian pre-dawn darkness. That data is still talking, still raising questions that the greatest planetary scientists in the world cannot fully answer. The real question is not what Cassini revealed in its final seconds. The real question is what is still hidden in that data that no one has found yet, and whether, by the time the next spacecraft reaches Saturn, we will have been wise enough to look for it.